Alrighty, let us continue on. There are a couple more problems I wanted to finish doing from the last examples of torque, and then I want to get into defining angular momentum, and then the next lecture will probably be some more problems on angular momentum conservation, just looking at my schedule on the whiteboard. Alright. 2 more lectures with rotation, and we're done with rotation. To review, we're playing around with Newton's second law for rotation, that the net torque on an object equals the rotational inertia times its angular acceleration. Torque plays the role of force, rotational inertia plays the role of mass, and angular acceleration plays the role of acceleration with rotation. This is defined. This expression is true for any rotation axis you define. Again, there may be an obvious one in the problem to use where objects are clearly rotating about a particular rotation axis, a ball on a string, for example. But you can put the rotation axis anywhere you want. And as long as you measure the torques correctly, as long as you measure the rotational inertia correctly, the angular accelerations you get will be the same. Again, remember that torque is defined as the moment arm cross the force being applied, such that the magnitude of the torque vector is the moment arm, the force, times the sine of the angle between them. Unlike the dot product, where it was the cosine of the angle. Perpendicular forces to the moment arm are what get things rotating. And then we had an example, we were starting examples on equilibrium and gravitational torque. And gravitational torque, even though gravity is pulling down on an extended object, the gravitational force is pulling down on every little bit of that extended object. You can quantify the total torque on an object by doing r cross the force due to gravity, mg, where the moment arm is measured out to the location of the center of mass. We can then define the conditions for equilibrium to be that there is no net force and that there is no net torque. Again, true about any rotation axis that you impose. So let's see, we had done the wine bottle open holder last time. Let's do a drawbridge now. Suppose there's a drawbridge that is lifted up, and there is some chain that connects it to the castle or whatever this is. Suppose the drawbridge is a 3 by 6 meter piece of wood with a mass of 2,000 kilograms and is currently lifted up such that it makes an angle of 60 degrees with the horizontal and is being held stationary by a chain. What is the tension in the chain that is holding up this drawbridge and keeping it stationary? Now it is being kept stationary. So we could think that there is no net force on the system, and that would be true. Another condition for equilibrium, static equilibrium in this case, where the velocity is 0 and is remaining 0, or the angular velocity is 0 and is remaining 0, is that there's no net torque on the system as well. So a way of establishing this might be to write down all the torques that are acting on the drawbridge, and using that to determine the tension in the cord. So in this case, the first thing you would have to do is establish a rotational axis. You're going to measure all these torques from some rotational axis. Let's use the one that makes the most sense, as in the one that the drawbridge would actually rotate about if the chain were to disappear. So we'll call that point into and out of the screen the axis of rotation. There is therefore, I'll even zoom in, there is therefore a moment arm that goes out along the drawbridge to the chain where there is a tension force pulling up on the drawbridge. So this is some tension force. It is some length. In this case, how long did I say it was? 6 meters. So this is some moment arm that is 6 meters out to some tension force that is pointing, in this case, perpendicular, the way I've drawn it, to the moment arm, which is nice and convenient. There is also a gravitational force that is pulling down on the wood drawbridge. And again, by gravitational torque, we will take the location of the force to be right at the center of mass of the drawbridge, in this case, right in the center of the drawbridge. In that case, there is another moment arm out to that force. Both of these, since they are not parallel or anti-parallel to their moment arms, exert torques on the drawbridge. And we expect that in equilibrium, the sum of the torques on the drawbridge better add up to 0. Which means that we expect the torque due to gravity plus the torque due to the tension to add up to 0. And the hope is that we can use these expressions to figure out the tension force. So now we have to figure out what these are. The torque due to tension, again, is going to be then the moment arm crossed with the tension force. If I use the right hand rule, my hand goes out along the moment arm, curls to then point in the direction of the tension force. It looks like that torque points out of the screen for me. So I expect this to be out of the screen. If I look at the gravitational torque, that moment arm again goes along the drawbridge, but then I have to curl my fingers to point down. So I can't do it like I did for the chain. I have to do it this way. So then my fingers, sweep downwards. It looks like in this case, the torque points into the screen. So this is again a one-dimensional problem in that the torques are only pointing in and out of the screen. So I can just add up their magnitudes with the appropriate negative or positive sign. Taking the convention that clockwise is negative, that means I expect into the screen for a torque that points into the screen. My right hand curling around my right hand gives me clockwise rotation. I expect I will have a negative sign for this torque and a positive sign for this torque. A way you can think about this is if there was only one force acting on the drawbridge, if it was just the tension force, that would want to make the drawbridge rotate counterclockwise. If it was just the gravitational force acting on the drawbridge, it would want to make the drawbridge rotate clockwise. So the torque from the tension is the moment arm, R, the tension force, and then the sine of the angle between them, but that is 90 degrees. So then this is just the length of the drawbridge times the tension force, and that's it. Sine of 90 is 1. And with a plus sign. If we think of the magnitude, I guess not technically the magnitude because we're going to have a negative sign here. So if we look at the gravitational torque, that is not the full length of the drawbridge, but it looks like it's R over 2 times the gravitational force, mg, times the sine of some angle between them. So we can look at the angle that is made between the moment arms. The moment arm looks like it's pointing out in this direction, and then gravity is pointing straight down, and this is the angle between them, which is greater than 90 by some amount. And I'll let you think about it, that this angle is 90 degrees plus 60 degrees. So then the sine of theta is the same thing actually as the sine of 30 degrees in this case by trig identities. Sine of 30 degrees is a half, so then this just becomes r mg over 4. All right, and we're going to throw a negative sign in front of it because it is pointing into the page. The sum of the torques then imply that RT minus RMG divided by 4 equals 0, which implies that T equals mg divided by 4. So the tension in the chain is 1/4 the weight of the drawbridge in this case. Now I could ask, let's go back up to the drawing. I could ask, suppose the chain breaks and the drawbridge begins to swing down. What direction does the angular acceleration and angular velocity eventually point? Because again, we want to work on our intuition for how these angles and these vectors describe the motion. So if the tension force were to vanish, the thing would start to rotate clockwise. So again, I could take my right hand and curl my right hand finger such that it rotates clockwise. And I can only do that if my thumb points into the page. So the angular velocity eventually points into the page. And that should make sense because we just said that the torque from gravity also pointed into the page. The torque from gravity pointed into the page. Therefore, if only gravity were acting on the drawbridge, the resulting angular acceleration would also point into the page, the F equals ma of rotation. The angular acceleration points into the page, so eventually the angular velocity will be parallel with it. Also points into the page. The drawbridge rotates clockwise. Plenty of room. Let's do another equilibrium problem. Suppose you have two scales and they are supporting a beam of wood that has some mass little m. And on top of that beam is a box of mass big M that is not perfectly at the center, but is slightly off center. And the beam is of length capital L. Each of those scales, each of those pivot points at the edges, are pushing up on the plank of wood that's holding the box by the assumption that nothing is moving. And the question is, if these were actually little bathroom scales, what would the reading of the force be for each of these? So said another way, how much force, if we call this scale 1 and scale 2, what forces are exerted by each scale? Again, this is in the assumption that if nothing is moving. We have static equilibrium. Now, static equilibrium means that I can look at each individual object, the plank and the box, and I must be able to say that the sum of the forces on each of those equals 0. Given we just had an exam on this, maybe it's worth even taking a moment to review. So the first one I might do is the big box, big M. If I define that as my system, I look at whatever is touching the box. So many people on the exam applied forces to an object that was no way in contact with the box or with the object. You have to be in contact in order for the force to apply at all. In this case, it is touching the bottom plank, which is pushing up on it. So I might call this force of the plank. The big box also has a gravitational tug pulling down on it with big mg. If I define up as positive, the sum of the forces equaling 0 then just says the force of the plank equals minus mg. Plus mg. Up is positive. Again, we arrive at that the sum of the forces means that there's a push up minus mg, and that equals no net acceleration. That's where that came from. For mass little m, it is being touched by the big box, so there is some force from the box pushing down on it. In this case, it will end up being just mg, but you can't just blindly say that it's equal to mg. There's also the force from the scale 1, and there's also the force from scale 2, pushing up on the wood platform. And then there's its own gravity pulling down. The sum of the forces equaling 0 then implies that n1 plus n2 minus little mg minus the force from the box equals 0. Now we can identify that the force of the box on the plank is the Newton third law pair of the force of the plank on the box. So this and this are third law pairs. Therefore, I can replace this with just minus mg by Newton's third law. Plus. Yes. So in this case, the two forces pushing up must be resisting the two forces pushing down. Its own weight is pulling it down, and it's also feeling a push from above from the force from the box. I guess these should have been capital M's. Anyway. All right, but notice this doesn't quite help us, because we are looking for this and this, even though we know everything on this side, perhaps. But we do not know, we cannot get N1 and N2 individually by this route. In that case, we have to work in the second condition for equilibrium, that the sum of the torques must also equal 0. But here's where we can be clever. The sum of the torques must equal 0 from any axis of rotation. Any green line, since I've been using green for axis of rotation, that we use, I can figure out all the torques from the point of view of that axis of rotation. And then that allows me to, that may allow me perhaps to isolate which of the forces, each of these individual forces. So let me redraw this. Actually, I'm out of room, so I'm going to move over and redraw. Scale 2, scale 1. There's a box over here. I think the box was a certain length. This was a length L over 4, where the entire length of the rod was L. Now I can say that the sum of the torques on the plank must be 0. If nothing's moving, there can't be any net torque on the system, where my system, in this case I'm saying, is the plank. Now there are 4 forces that we identified that are acting on the plank. Its own gravity, the weight of the box, and then the 2 normal forces from the scales. What I would ideally like to do is only get one of those scales in the problem. If I were to put my axis of rotation, maybe this is my axis of rotation 1, my first guess for the axis of rotation. I can then measure the sum of the torques from that axis of rotation and set it equal to 0. In this case, there's gravity pushing down from the big box, and it has some moment arm. There's the normal force pointing up, and that has some moment arm. And then there's this normal force pointing up, and that has some other moment arm. So I might say that, the big box, big mg, my hand goes out to the box from the axis of rotation, sweeps down, my thumb points out of the page, which is counterclockwise motion. So I would say that torque looks like it's plus big mg. There's the gravity of the plank itself, but that is located right at the axis of rotation. Sorry, this is not just mg, but this is mg, and then I suppose this is L over 4, because that's the length of the moment arm. And then they're at a 90-degree angle from one another. The weight of the plank itself does not contribute, because it is located at the axis of rotation. There is no moment arm. But then there is the normal force from scale 1, which is a length L over 2 away. Then there is the moment arm, and that wants to make things rotate, looks like clockwise. And then for moment 2, that wants to make things rotate counterclockwise. So I might get an expression that looks like this. There are 3 torques from this rotation axis, and that is the expression between them. Notice, however, this doesn't help, because both normal forces are still in the problem. I want one of them to go away so I can uniquely solve for the other. In this case, I would say, pick a different rotation axis such that one of them doesn't contribute to the torque. So maybe I'll put my axis of rotation here. scale 1, scale 2. In this case, there's a torque from the weight of the plank itself. There's a torque from the big box. And there's a torque, oops, wrong way. There's a torque from the first scale. It must still be the case that the sum of the torques equals 0 from this rotation axis. Else, from the point of view of that rotation axis, things will start to rotate. So in this case, it looks like the two weights, big mg and little mg, they're at a 90-degree angle. That's good. Sine of 90 is 1. And they want to encourage what looks like counterclockwise rotation, because if I do the cross product, my thumb points out at the screen. So that looks like it's big mg plus little mg. And then if I do the cross product, moment arm goes out to scale 1, my fingers wrap up, my thumb points into the page. That looks like it's, I did it again. I keep forgetting the moment arm. So little mg looks like it's a distance L over 2 away. Big mg looks like it's a distance 3 over 4 L away. It's 75% of the way out. And then the normal force is a length L away. Those are the three torques from that rotation axis that I can then set equal to 0 by assuming equilibrium. And look, how nice is this? The L's go away, and I can just simply write down that N1 equals what looks like little mg over 2 plus big mg over 4. 3 big mg over 4. By choosing an axis of rotation where one of your unknowns resides, that means from that axis of rotation it does not contribute to any torque. And it allows you usually to isolate one of the other unknowns in this case. You could then solve for N2 in a variety of ways. You could go back up to one of the various expressions we had, plug this, now we have N1, we could plug that in and solve for N2. You could, of course, do the same thing again, but instead put the axis of rotation at the other normal force. In that case, the box contributes a torque, the plank itself contributes a torque, and the other scale contributes a torque. So in this case, it looks like it's big mg, then it's L over 4 away from this new axis of rotation, minus little mg L over 2, because it's halfway out, and then plus N2 L equals 0. In this case, the L's go away. And this expression simply becomes that N2 equals, looks like little mg L over 2. Sorry, the L's went away. So that's just mg divided by 2 plus big mg divided by 4. And if you notice, this is less than the one on the left-hand side, which if you think about it makes sense, because more of the mass is located closer to the scale on the left. So that scale has to do more to resist the weight underneath it, compared to N2, where it's farther away from where all the mass is. So the scale reading on that edge of this table, this scale table, would be slightly less. So again, the takeaway here is that we can use the equilibrium conditions, which is the sum of the forces equals 0. Sometimes that works. Some of the torques must also equal 0 from any rotation axis. So you are free to put down a rotation axis that makes the most sense for you. usually you can do it such that you eliminate one of the variables in the problem. So you'll have a homework problem that's doing exactly that. Okay, that is all I wanted to do on torque. The final piece. We've done masses, we've done kinematics, we've done forces. Energy is nice because energy is just global. It doesn't matter what you're doing. Energy is energy. But we saw that we could define kinetic energy as both a rotational part and a translational part. Something rolling down a hill has both energy in that rotation as well as the fact that it's moving at all. The only thing left is now some sort of quantity like angular momentum. To remind ourselves, before we had regular momentum, which was the mass times the linear velocity. We had a result that the sum of the total momentum of the system, how that changes with time, is the result of external forces on the system. The total momentum of the system changed only when there were external forces on the system, such that if there was no net external force, linear momentum was conserved for your system. Is there an analogy now that we can make with angular momentum? There is. So physically, we can think that if momentum was this quantity that we use in order to understand how much oomph something had in a particular direction. It incorporated both their mass, the inertia, and the velocity into the system, such that if something was really moving in one direction, right, how easy or hard it would be to stop was a measure of how much momentum it had. If something is now rotating, be it spinning in a circle or rotating around a larger circle, how you stop it from, or if I were to wanted to change this sort of rotation, I would have to apply torques to the system. And the question is, how can we quantify this as some sort of quantity that measures the oomph something has in rotation? So let's define the angular momentum, which using your book's notation is just little l. About a rotation axis as we're going to say the vector L is going to be defined as r cross the actual linear momentum, or r cross mv, or just like what we saw with properties of the dot product, scalar constants can come out, can fly around inside the cross product as it wants. Similarly, we could bring out that mass and just say that this is the mass, and then multiply by the cross product of some sort of moment arm cross the velocity. Where again, this is measured from your pivot point, rotation axis, what have you. The units of angular momentum, therefore the unit of mass times the unit of position, times the unit of velocity. So this is kilograms times meters per second. So kilogram meter squared per second. It does not have a special fancy name. So here's an example. Suppose you have some coordinate system where I'm going to define my kind of pivot point, my axis of rotation, just as the origin. So maybe my pivot. And I have some particle out here that is moving with some linear velocity in this direction, and it has some mass. I can draw from my pivot point a vector that points directly to that particle, and that defines the moment that corresponds to this. This, of course, keeps going, and I could define some angle between them if I wanted. And the way you evaluate the angular momentum is, again, via the cross product. You put your fingers along the moment r, and then you curl them so that they point in the direction of v. In this case, the way I'm looking at it, if I do so, then L points, in this case it looks like points into the screen based on the right-hand rule, with a magnitude equal to the moment arm times the momentum times the sine of the angle between them. Or again, m, the moment arm, the velocity, the sine of the angle between them. Gives me a measure of the angular momentum. If I have, say, 3D motion, where I have the xy plane, z direction, and suppose I have something, maybe the xy plane is a table or something, and I have a ball on a string rotating about some table. Or maybe here at this point there's some velocity v that it has as it rotates around, in this direction. I could evaluate the angular momentum about, say, the origin or some pivot point, something, as drawing my moment arm out to the velocity. And then in this case, if I imagine this, if I do r cross v, takes a little bit of spatial reasoning, but in this case I would argue that the angular momentum points along the z-axis. So I need a new color. Maybe I'll do blue. Where the cross product of those will be an angular momentum vector that points along the z-axis. And you can practice and convince yourself of this. And again, just like the momentum was saying something about the tendency for an object to continue moving in a particular direction, right? It has some velocity, but in order to change its velocity, you have to overcome that inertia or mass. The angular momentum is saying something about the tendency for something to continue rotating in a particular direction. Again, this is really only useful if perhaps we can say something about how its properties might be conserved or passed from one object to the other through torques. So the goal for me today is to essentially write down all the main results and then just do problems in the next lecture. Because I will admit, angular momentum is probably the most abstract of all of these weird rotational vectors. So here's another example. Suppose that the origin is the sun, and then the Earth is rotating around the sun in a counterclockwise fashion. If you had to define the angular momentum of the Earth, what would you write? So in this case, given the location I've drawn this, right, there's some moment arm. Then I imagine that the Earth is moving with some velocity v. So then again, if I do the cross product of r cross v, which is the definition of angular momentum, well, actually it's r cross p, but the mass is, right, it's m times v, or really it's the m, the moment vector across the velocity vector. R cross v, if I do it the way that's drawn on the screen, my thumb points out of the screen. So then I would say L points out of screen. I could also ask, if the Earth is going in a counterclockwise direction, what is the angular velocity point in? I think we can now see if I curl my fingers in a counterclockwise rotation, my thumb again points out of the screen. It also points again, counterclockwise rotation usually is associated with a vector that's pointing out of the page, if out of the page is perpendicular to that motion. And the angular momentum, of course, is pointing in the same direction. The angular momentum is quantifying the tendency for something to keep going in that counterclockwise direction. Torques are needed to change the direction if we want to change. Let's see exactly how it changes. So I'll draw this in 2D, but of course we could, this applies in any direction really, or any dimension really. If there's some velocity, and I have some moment arm that is out to the object from some pivot point, or some axis of rotation, say, I can define the angular momentum as, and the object has some mass, of course, I can define the angular momentum as r cross v, all multiplied by m. In this case, very quick, it would point into the page, based on how I've drawn it. Before we said linear momentum change as a result of external forces. How does angular momentum change for a given particle? That therefore is just the derivative of the definition for angular momentum. Let's not do anything too crazy and assume that the mass is remaining constant, so let's bring that out. So then it is the derivative of this cross product. For the dot product, well, for regular products in Calc 1, we saw that there is a product rule for derivatives. We saw that the product rule applies for the dot product itself. Perhaps unsurprisingly, the product rule also applies for cross products. So I could write this as dr dt cross v plus r cross dv cross dt. However, dr dt is just v, and dv dt is just a. Now I can immediately say something about one of these terms. We saw this in the previous lecture for one of the rapid fire questions. A vector crossed with itself is 0. This is just 0. because the angle between them, between v and itself, is 0, and the sine of 0 is 0. So then this is just mr cross a. But just like how I factored the m out, I can put it back in. This is r cross m times a, mass times acceleration. Or look at that, r cross a force. If forces, and also, well, I guess we can go even further. R cross F, that's just a torque. Forgot the last fundamental step. Torques change angular momentum. That's the takeaway here. Really, I should say external torques. Change angular momentum. Change angular momentum. Notice we're seeing the same exact thing that we saw for linear momentum. Linear momentum changed as the result of external torques external forces on the system. Because everything inside the system, by Newton's third law, there was no net change in the overall momentum. Angular momentum, same sorts of things. External torques from the system change the angular momentum. Because if there were internal torques between objects inside the system, again by Newton's third law in angular form, the torques would be equal and opposite. So for a system of particles where we could define big L as the sum of the individual angular momentums of each, if there are a bunch of particles rotating around, I could calculate the total angular momentum. And then just like what we saw with regular momentum, we can say the total angular momentum changes as the result of some external net torque. I'll just write on the side. Remember what we had said before. The total change in the linear momentum was the external net torque, or net force. So again, the analogies continue. Angular momentum obeys the same sort of relationship as regular momentum did through this definition. Such that if the external net torque on the system equals 0, that implies the rate that the total angular momentum is changing is 0. That implies that the total angular momentum is a constant. In this case, really, that's a constant vector. Which is what? Which is nothing more than the conservation of angular momentum. Also worth a highlight. Just how total linear momentum is conserved if there's no net force, total angular momentum is conserved if there's no net torque. And we've completed it. We've completed the 3 conservation laws. Where we say no net external torque implies L is a constant. Angular momentum is conserved. No net external forces. The total linear momentum is a constant. no non-conservative forces. And really no external forces either. But as long as you restrict yourself to always conservative forces, or I guess external, implies that the total energy is a constant. I guess we were using T, weren't we? You know, these three laws are kind of the big takeaways of this section of the course. That there are quantities, energy, momentum, angular momentum, which as long as certain properties are obeyed, certain conditions are met, then these are quantities that you can think of as there being some finite amount that is passed around to objects, either through work being done for energy, through impulse for linear momentum, and I guess angular impulse for angular momentum, which is the result of torques. Linear momentum is the result of forces, and then energy is the result of forces doing work. Now let me make one last comment on angular momentum, and then again the next lecture will just be problems. There is something that's nice that we can say for extended objects. So objects that are not just individual points, but spheres, balls, ice skaters that are spinning in circles. And this gets to a point which you might have raised an eyebrow about, where we've been doing this entire thing where we've been saying everything's analogous in rotation. But then I defined this weird angular momentum cross product thing, where you might have thought, if it was perfectly analogous, then why didn't this translate to something like I omega? If, rotational inertia is the analogy of mass, angular velocity is the analogy of regular velocity, why was this not the definition of angular momentum? Turns out, for special cases, it is. If your rotation axis is fixed, so you're not worried about the rotation axis itself moving around. If you fix your rotation axis, you're just worried about how rotation is occurring about some axis of rotation that's not moving around. Then it turns out, and your book kind of sketches out this proof, so I'll let you just read the book. Then you can write, indeed, the total angular momentum of an extended system which has billions and billions of little particles, which you might evaluate that by doing something like R cross V dm and adding up the cross product of all those individual little mass particles. You can show that this ends up just being the rotational inertia times the angular velocity. The analogy does hold for extended objects where your rotation axis is not budging. So that in those cases, if L is a constant, if angular momentum is conserved for these extended objects where your rotation axis is not moving, an example could be an ice skater spinning with her arms out that she then brings her arms in. She spins at a different rate as a result. We'll do that problem in the next class. But if angular momentum is conserved for these extended objects, then you can say something like I omega initial equals I final omega final. Right, you can take I omega initially for the system. Maybe it's the ice skater with her arms outstretched. Then you can evaluate I final omega final when she, say, pulls her arms in. Her rotational inertia has changed as a result. She's bringing more of her mass closer to her axis of rotation. And as a result, she spins faster. Her rotational inertia went down, so her angular velocity has to increase, such that the total angular momentum is constant. All right, good. We will do problems related to this for the next lecture.